Good morning, dear children, and welcome to yet another session of Vistaslearning. My name is Denzil, your science tutor for class 9. So today we have a fascinating topic to discuss. A very interesting and very easy topic. So the topic is based on motion of objects under the influence of Earth's gravitational force. This is a session 4 of the chapter Gravitation. So let's conduct a quick audio test and a video test because this is a live session. So go ahead and give me a thumbs up if I'm visible and audible to you. Right, so let's look into the comments. So let me conduct the audio and the video test for myself. Yes, I'm visible. So let's conduct the yes. Excellent. So there's no problem with audio and video quality. So let's move ahead with the session. So for today's chapter, first we recollect what we have dealt in the last session. In the last session, we tried to calculate what is the acceleration due to gravity, and that is where we left off. I gave you that as a homework where you're supposed to calculate the acceleration due to gravity of Earth. Now let's get to the calculation. Now first, we understood what the expression is in order to calculate the acceleration due to gravity of Earth. And that expression is given by quick change in the color, G equals to Gm by R square, where G is the acceleration due to gravity, capital letter G is the gravitational constant, M is the mass of the object. Here certainly we are going to determine what is the acceleration due to gravity of Earth, so mass of Earth. Re is the distance of separation between two objects, but since we are trying to determine what is the acceleration due to gravity of Earth, we find the radius of Earth. So naturally G, Me and Re are constants. So I have made a note of this constant, so you can make a quick note of this in your notebook. Mass of Earth is about 5.98 into 10 raised to 24 kilograms. Radius of Earth is 6.37 into 10 raised to 6 meters. And the gravitational constant has a value which is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Now all we need to do is take these three parameters and substitute in the given expression to find the value of G. And surprisingly, what you'll notice is the value of G will turn out to be 9.8 meter per second square. Interesting. So now this is how you can identify the acceleration due to gravity of any planetary objects given under the circumstance that you know the mass of the planet and also the radius of the planet. Similarly, you can also determine what is the acceleration due to gravity of the Sun. Again, by noting down what is the mass of the Sun as well as the radius of the Sun. Now here's an interesting fact. The last class I told you as well, we solved a problem of a polar bear. And I told you that the acceleration due to gravity at the poles is 10 meter per second square, whereas at the equator is 9.8 meter per second square. Interesting. So if mass and radius are constants, then how can a gravity change at two different places, at the equator as well as at the poles? How can there be a difference in the acceleration due to gravity? Shouldn't it be a constant? Let's answer to that question. Now in fact, if you look at the shape of the Earth, it is not completely spherical. Interesting fact. Earth is not completely spherical. We call the structure of the Earth, the shape of the Earth, as an oblate. What is an oblate? Not your omelette that you make every morning, but think of the egg that you choose. The egg, the shape of the egg, which is oval in shape, that is how an Earth would look like. Interesting. Earth looks like an egg. Certainly I disagree with you, sir. No, that is a true fact that Earth is sort of oblate, squashed at the top, bulged at the sides. Now what happens in case of radius? Now the radius in case of at the equator the radius is greater than the poles. Oops. So let's call that R1 and R2. Certainly in this following case that R1 is greater than R2. If the radius is greater, then what happens to gravity? So you have a denominator that increases, then the acceleration due to gravity decreases. And if the radius decreases, then the acceleration due to gravity increases. So in the following case, R2 is smaller. Since R2 is smaller, then what happens to G value? Increases. Therefore, G value at the equator is 9.8 meter per second square and G value at the poles is 10 meter per second square. Not much of a difference, a very small insignificant difference that you can see, but even a decimal is a very important for a physicist and a mathematician. A small decimal places, the decimal values matters a lot to us. So this is how you can identify the acceleration due to gravity of any planetary celestial objects, you can say, as a whole. So now coming to the first chapter, the first or second chapter where we discuss Newton's laws of motion or equations of motions. There were three equations of motions that we dealt with. The three equations of motions being V equals to U plus AT, S equals to UT plus half AT square, and V square equals to U square plus 2AS. Now make a note of this in your notebook, though we have discussed in the chapter 1, if I am not mistaken, in the chapter 1. So we have discussed how to derive each and every equation. So make a note of this, the couple of changes that has to be made. Why the changes has to be made? Now the acceleration, particularly what you are looking at, is the acceleration for an object which is moving in a linear position, and also certainly linear position along the horizontal direction. Now we have to discuss an object that is falling vertically downwards or moving vertically upwards under the influence of gravity. How is that possible? So what are the changes that we are going to discuss? So once you have made note of this, now we make those little bit of modifications which is under this equation of motion under the influence of gravity. Now for an apple, a quick look at the comments. Rakesh, you are looking very smart, sir. Thank you so much, Rakesh. Rakesh, lovely. Okay, not really sure as to why. Oh, you call me lovely. Okay, thank you so much. Mathematics, you're looking very cute. Thank you so much. Good morning, Rakesh. Good morning to you. Goldberg Spear is here. Hello, Mr. Goldberg. Welcome. Good morning to you, sir, or good night to you, sir, since you're living in a different time zone. Goldberg Spear, wow, sir, you look great. Thank you. I've got a nice clean trim. So yes, I've lost all my beard. In fact, what had happened is that someone stole my beard. So I cannot retrieve it anymore. Goldberg Spear, it's all about gravity. All right. Goldberg Spear, your name is not good. Okay, I have no comments regarding that. Ashwant, very good morning to you. Right. So equation of motion under the influence of gravity. Couple of modification for the equation of motion. Now for an object, let's say for an apple which is present here. Now when this apple is let go, what you observe is that the apple falls to the ground. And as the apple falls to the ground, its velocity increases. Since its velocity is increasing over a period of time, which means it is accelerating. Now, the acceleration here is certainly positive. So, it has a positive acceleration. So, since it has a positive acceleration, the acceleration is nothing but acceleration due to gravity. So, acceleration due to gravity should also be positive. So, in the previous where we notice A, in places of A, we will substitute with acceleration due to gravity. So, apple falls, positive acceleration for a downward motion, you have V equals to U plus GT. Notice how we replace from A to G, because here since the object is under the influence of gravity, we have replaced that A with G. Next, S equals to ut plus half gt square, and also V square equals to u square plus 2gs. So, I hope I have made this easy for you. For objects that are falling, you have positive acceleration, therefore, g is positive, and you have in places of A where g is replaced. Similarly, let us look at the case for an object that moves upward, meaning you take an apple and you throw it. You see that? So, in this case what you notice is when you throw any object upward, it slows down. Eventually, when it reaches its maximum height, what is the velocity at that point? 0. So, when you throw an object, when it reaches maximum height, then the velocity will be 0. So, which means here we have object that is slowing down, meaning you have negative acceleration. This negative acceleration also has another word which is called deceleration or retardation, but we will just call it for now, which is negative acceleration. So, since it has a negative acceleration, g, which is acceleration due to gravity, will be negative. So, you have negative g. Now, for the equation of motion, we have to replace that A with negative g. Therefore, now moving on, for an object that is projected upward, that is thrown up vertically, first we have V equals to U minus GT. So, you notice in place of plus A, now it is replaced with minus G, that is because you have negative acceleration. Similarly, S equals to ut minus half gt square, and why is it minus half? Is because of negative g. And the last one, can you guess what the last one is? Just as you guessed it, is V square equals to u square minus 2gs. All right. So, why is it important for us to learn these equations of motion for object that is falling to the ground, for the object that is moving up? Let us take a look at it with an example. Here is an example. This question is also from your NCERT textbook. So, you can refer to your NCERT textbook, question number 15, okay, as it is mentioned. So, it says here the stone is allowed to fall from the roof, from the top of a tower 100 meters high. At the same time, another stone is projected vertically upwards from the ground with a velocity of 25 meters per second. Calculate when and where the two stones meet. So, let me break this problem down for you. So, you have one stone that is dropped from top of a tower. So, this is a leaning tower of Pisa, which is located in Italy. So, one stone is dropped from top of a tower, the other stone is thrown from the down. Simultaneously, one is dropped, the other is thrown up. The other is thrown up with a velocity of 25 meters per second. Now, when you're dropping a stone, what is the initial velocity of the stone? 0, because it has no velocity as you drop. But once it falls to the ground, it has a certain velocity. So eventually what happens is, when these two stones move, the two stones will meet at some point. Okay, so let me choose a color. So let's say this is a point where the two stones meet. Now you need to find what is the height. Where is it given? Calculate when and where the two stones will meet. So what are the initial things that are given to us? Height of the building, which is 100 meters. Now to find the when and where, first where will locate it by this arrow, the yellow arrow gives an indication where the stones will meet, but also we need to find the when the stones will meet. Okay? Now I thought I would give you this as a homework problem. Let me see the comments. Goldberg sphere, 2 kidneys is equals to 1 iPhone 13. Guys, we are not talking about iPhones and giving away kidneys. Please focus. All right. My kidney is expensive. What is happening? Like I can get three iPhone 13 in one. Please don't fall for that hoax where you have to sell your kidney for an iPhone. There's a lot more than just an iPhone. In fact, you can become the next owners of another mobile company. So you don't have to rely on iPhones. All you need to do is focus on the concepts here, learn them and implement. Okay, so Goldberg wants your kidney. Mr. Goldberg, you already have 2 kidneys. You can work with that. Try not to take someone else's kidney. Rakesh, I think I've made it clear for Mr. Goldberg. You don't have to worry about your kidneys anymore. All right. Oh, this is a good question by Rakesh. If I throw myself, will the gravity be 0? Interesting fact, Rakesh. Yes, that's a good question. If you throw yourself, will the gravity throw yourself as in if you go on a skydiving? Let's say take an example of skydiving. So in a skydiving, is the gravity 0? Interesting. And also let's take the case of astronauts in space. See, now you have gravity, Earth's gravity, which is acting on the moon. Similarly, Earth's gravity should be also acting on the International Space Station, which is about 200 kilometers off the ground. So it is flying over our heads, which is 200 kilometers overhead, but then why aren't the astronauts falling? Does that mean these astronauts are experiencing a 0 gravity? Good question, Rakesh, but I want you to go ahead, explore, conduct a little bit of research, and I will reveal those answers. Okay? So you try to tell me, why doesn't the astronaut experience the gravity? Do they experience gravity, yes or no? And if they are not experiencing gravity, then why? And if they are, then why? Okay? So keep that in mind. Mr. Goldberg. All right. Because there's also a concept where we come across all about, free fall, how astronauts experience gravity, even though, so I've technically revealed the answer. Yes, the astronauts are constantly falling to the ground, but they experience what is called as weightlessness. So go ahead, conduct a little bit of research on this particular term, which is called weightlessness. Okay? So go ahead, conduct a little bit of research on weightlessness. So that will provide you more information as to why these astronauts feel as though they're not experiencing any gravity, even that they are. Okay? Right. So shall I leave this as your homework problem? Now, do you all want this question as your homework problem, or you want me to solve for now. If a sun's gravity is more, why Earth is not going inside? That's a good question, Rakesh, but if you go to my first few sessions, okay, the first 2 sessions, there I've explained to you why moon does not fall to the Earth. Okay, so the same concept can be utilized why Earth does not fall into the sun. So go ahead and watch the first 2 sessions of mine. There I explained to you why moon does not fall to the Earth even though there's Earth's gravity acting on the moon. All right. So let me do one thing. I'll leave this as a homework to you. So try to answer this question by using the equations of motion that we've modified for objects falling under the influence of gravity. Okay. Even you have gravity, should Earth go inside you also? Okay, now we have interesting set of questions. So now we're getting to topic mathematics. Even you have gravity, should Earth go inside you also? Now yes, technically yes, you exert a gravitational, you yourself exert a gravitational pull as well, but then compare the masses, your mass and the Earth's mass. Way big difference, right? So it is in the order of 10 to the power of 24 kg Earth's mass, and your mass is just about, let's say if you're 30 to range of 30 to 50, 30 to 60, I'm just guessing. So taking a big hit, 30 to 60. Now compare yourself with that many zeros with just 30 to 60 kgs. So Earth is more massive, therefore it has more gravitational force. So I've made that clear, yes? Mr. Mathematics. I still don't understand why is it Mr. Mathematics. I really miss Boogeyman though. Boogeyman entertained me. All right. The next one is understanding the difference between mass and weight. It's very common that if you have to go on a weight loss program or any of the weight loss programs, what you notice, what they say is lose weight now. It's a very wrong misconception. It is not the weight. Because why? Weight, we will learn soon, weight is so different from a mass. In fact, the wrong term, which is lose weight now, it should not be lose weight, in fact it should be lose mass now. So what is exactly mass and a weight? For a mass of an object is the total amount of matter that is contained in an object. So how much of material, how much of matter is present in oneself or an object is what we call as a mass. On the other hand, weight of an object is the force with which it is attracted towards the earth. Now when you say my weight is, let's say, 90 kilograms, my weight is 90 kilograms. 90 kilograms does not mean the same as the mass. In fact, if you're 90 kilogram, then your mass would just be 9 kgs. Interesting fact. How is that a 90 kilogram weight can be just 9 kgs? Now let's look at it by writing the equation of a weight. Weight is nothing but a force, and force we define by F equals to ma. But since there's a force that is acting on us, which is nothing but the gravitational force, so A can be replaced by acceleration due to gravity g, where F is equals to m into g. The following force is called weight, where weight equals to mass times gravity. So this is how you express weight, where weight is equals to mass times gravity. Now let's take the case if you're weighing, let me use another color, white. Okay, let's take the case where your weight is 90 kilograms. Okay, weight is equals to 90 kilograms. In order to find how much of mass there is, all we have to do is take this weight divide by the gravitational acceleration due to gravity of the planet, but in this case we are taking Earth because you are trying to find what is the weight on Earth. So, which means weight can differ in different planets. We will soon see that how weight is different in different planets. Though the weight is different in different planets, you will see that mass will remain the same in all the places. No matter any place you move in the universe, your mass will be the same unless you enter into a black hole where all your mass is stripped away. So, W by G, let us take if G value is 10 meter per second square. So, you can identify what is the mass, where mass equals to W is 90 divided by 10, where 0, 0 cancels. So, you get mass which is equals to interesting, isn't it? So, you get mass that is equals to 9 kg. Oh yes, since this is a force, weight is a force, you cannot express it in kg, we usually express it in newtons, all right. So, it is important that we express it in newtons. Okay. So, this is how you can identify the mass. Now, moving on, let us try to determine what will be our weight on the moon. So, how do we measure our weight on the moon? Now, for that, a quick equation. Now, the two ways you can express a force, one way which we did was mass times the acceleration. The other way you can express a force is by using F, that is equals to G m by r square. I hope you remember this, which is called by universal law of gravitation. So, similarly what I have done here, since this force is nothing but a weight, so weight of Earth, WE, weight on Earth is equals to G mass of Earth times the mass of object divided by the radius of Earth. Similarly, I have also taken for a moon, the weight of the moon is equal, weight of the object on the moon is equals to gravitational force times the mass on the moon, mass of the moon, mass of the object divided by radius of the moon. Now, by dividing one another, by taking this and dividing each other, then I get this following equation where weight of the Earth divided by weight of the moon is so. Now, mass of Earth, radius of moon, mass of moon, radius of Earth are constants. So, these constants I have put it here for your reference. So, you can make note of these constants where mass of Earth, mass of moon, radius of Earth and radius of moon. Make a note of this constant. Next, we substitute them in the following equation, and then what we observe that the ratio of the two, where the mass of the weight of the Earth by the weight of the moon is 1/6. It means that if you weigh 1 kg here on Earth, then on the moon it would weigh about 1/6 of that of Earth. So, that is the difference where you can write weight of Earth, weight on Earth is 1/6 of the weight on the moon. You see here how the weight can change from a planetary object from one planet to another planet. Similarly, we can also find what is the weight on the Jupiter for a given planetary object which is so massive. The acceleration due to gravity on Jupiter is approximately 25 meter per second square, right? Now, if an object weighs 4 kilograms here on Earth, if an object weighs 4 kilograms here on Earth, what will be the force on the moon, the weight on the moon? In that case, we write weight which is equals to mass times acceleration due to gravity. Let us not take it g, here in this case we have acceleration due to gravity of Jupiter Okay. So weight, which is equals to 4 kilograms times 25, where you get the weight equals to 100 newtons. So massive, 4 kilograms, which experiences 100 newtons. All right. So you can go ahead and explore more on this, where for a given planet, I've mentioned what are the different acceleration due to gravity. So you can make note of it and try to identify what would be the weight on different planets. Okay. So quick look at the comments. Can I take a class on black hole? But that would, please take a class on black hole. It would be 6 times less than the Earth. I know, very good. You have written ulta. I have written ulta. What's ulta? What's written ulta? I don't understand. What is ulta? Oh, you mean this one? This one's ulta. Okay, I think it's supposed to be J, acceleration due to gravity of Jupiter. So if you put J, I think that would make more sense. If that's what you meant, I hope so. Ulta. Oh yes. I see what you mean. Yeah, I see what you mean. 1/6. Yes. Thank you for reminding me. Yes, thank you for reminding me. Here, it's supposed to be the other way around. Okay, so it's supposed to be 6. All right, where you get weight of the moon is 1/6 weight of the Earth. Thank you so much, Rakesh, for pointing out that. Yes, it is supposed to be 6, not 1/6. Thank you for pointing out that. It's supposed to be 6. So where you get weight of the moon is 1/6 of the weight of the Earth. Yes. All right. So quick correction here. Thank you so much, Rakesh. Yes. All right. So now we come to the last section, which is a car problem. Now, when you have to push a car, you find it really hard. Why is it hard to push a car? Though the gravity is acting in a downward direction, you're not trying to lift the car, you're just trying to push the car. So gravity is acting downwards, but you find it hard to push the car in a horizontal position. So why is it difficult to push a car? So let's see the answer. So this answer to you will, do I reveal it now or do I reveal it in the next section? I'll give you some time to think about it, so I'll reveal it to you in the next section. So keep your answers ready. So we will again discuss why is it hard to push a car even though the gravity is acting in a downward direction, not in a horizontal. Gravity is acting downward direction towards the center of the Earth. But still you find it very hard to push the car in a horizontal direction. Again, you are not trying to lift the car, you are pushing the car. Okay? So if you've enjoyed the video for now, make sure you give a thumbs up, subscribe, and also click on those bell notification. Do visit us at www.we-learning.in to further stay tuned. Get more details about the classes ranging from class 1 to class 12. So kindly go ahead, share with your friends, your family members, and let those people know who are in need, who are in the board exams as well. So you have board, sessions where you have 10th standard and 12th standard sessions that are conducted. A very important part of life. So we will discuss a couple of answers to the homework problem, and also in the next session we will be dealing with force and pressure. So I'll see you all in the next session. Until then, everyone,